Appearance of developed cavitation with comparatively low speeds of the experimental cart with a model can be achieved by forced air supply to the stall region of the flow behind cavitated disc. In this case, we talk about artificial cavitation or ventilated cavities. The flow pattern with developed cavitation is defined by cavitator's size and resistance, its speed of movement V0, pressure in the undisturbed medium P0, and pressure in the cavity Pk. The surface of the cavern adjacent to the cavitator over a significant distance has smooth and clear outlines, transparent. In the tail region occurs the destruction of cavity's walls, forming diphasic foam-like mixture. The similarity of developed cavitational currents is established with dimensionless criteria. The defining criteria is the cavitation number, which is a ratio of difference of pressures to velocity pressure. The Froude number plays an important role as well, showing a ratio of inertial forces to hydrostatic forces. The volumetric flow rate of the booster gas affects the value of the cavitation number. We'll set the Froude number to be constant. At low gas flow rate, cavitation number is high and cavity has small dimensions. Increasing gas flow rate leads to decrease in cavitation number and therefore increase to overall dimensions of the cavity. Further increase in gas flow rate maintains the noted tendency. However, there exists a certain minimal cavitation number, which cannot be reduced by any increase in booster gas flow rate. Further increase in the flow rate leads to the destruction of the cavity's walls. Gas is carried away from the cavity either in portions along annular vortices, which corresponds to high cavitation number, or along longitudinal vortices, which corresponds to low cavitation number. The latter case is typical only for ventilated cavities. Ventilated cavities are also studied in hydraulic flumes, using principle of reversal of motion. The tail regions of horizontal cavities float in a heavy liquid. At a small Froude number, which is now set to 3, the emergence of the cavity is large. As the Froude number increases to 10 and 15, the floating gradually decreases. And at a Froude number equal to 25, the cavity takes on a practically axisymmetrical shape with an almost horizontal axis. When the cavity axis is oriented vertically, radial deformation of its sections occurs. The tail region expands as if floating up. The overall length of the cavity decreases. The frames obtained by high-speed filming demonstrate cavities in the vertical flow, behind the disc, and cone. Setting the cavity to disc at an angle of attack disrupts the axial symmetry of the flow. The axis of the cavity is curved. The normal force N decreases proportionally to the cosine of the angle of attack delta. The resistant force X is proportional to the square of the cosine of the angle of the attack. The asymmetry of the flow causes the appearance of a vertical component of the hydrodynamic force Y, called the lift force. The vertical oscillations of the disc are accompanied by wavelength disturbances of the cavity surface. At the bottom of the screen is a stationary cavity. The non-stationarity of the cavity surface can be caused by pressure pulsations in the cavity. A consistent increase in pressure leads to a periodic thickening of the cavity. The overall dimensions and shape of the cavity depend on the resistance of the cavitator, which in turn is determined by the shape of the latter. The screen displays images of cavities, sequentially, behind conical cavitators with different sharpening angles. The cavitation and fruit numbers are the same in all cases. As we can see, the smaller the sharpening angle, that is, the lower the resistance, the smaller the overall dimensions of the cavity.